Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Synopsys with Ribhu Mittal, who's going to talk today about some of the complexities that are going on in debug and what's changing. So Ribhu, obviously things are getting more complex, designs are getting bigger, there's a lot more going on in them. What does this mean for debug? What has to change?
So working with customers across the board, as you said, that I'm seeing a growth in design size. And on top of that, I'm also seeing growth in the contents that are being run on emulation. And what we are seeing is that the traditional methods through which debug is being done is leading to long time to root cause. And that's what we are trying to address.
This is not a new problem, right? We've been running faster at every single node since quarter micron and even beyond that. What's changed now?
So the key thing that is different is that as we are able to get to faster chips, that means that we can bring in a lot of software contents into the design cycle, which we were not able to do before. And so with the growing complexity of the software contents and the whole shift left of the validation cycle, we need to come up with new solutions how to reduce the turnaround time to debug a problem.
Why don't you draw this out for us?
Yes, let's get to that.
What are we looking at here?
So this picture that is drawn here, it is fairly simple. On the x-axis, we have the software complexity, and on the y-axis, we have the design complexity. And in modern design, what we are seeing is that designs are getting bigger and bigger, and they're going up to 1 billion gates, more than 1 billion gates. And then the contents are also getting longer, and we have test cases that are running for billions of cycles. And as you can see that the trend has been in this direction, right? So starting with the subsystem and IP and all the way going to AI, GPU, networking designs, we are seeing a confluence of bigger designs running long test cases.
So why don't you give us an example of this? What happens in the real world?
Okay, so actually here is a picture of a very common example that we see with multiple customers. And here I have a case of an application running in emulation. So design goes through reset, we do OS boot, we set it up for some application, and let's say that in this case I've done the Windows boot and I'm running Internet Explorer. And while doing something in Explorer, my OS hangs. Now the problem could be because of a cache error that happened during the boot itself. And from the error to the first sign of failure, you've gone through billions of cycles. So now debug has become challenging in the sense that you have to traverse back so many billions of cycles to find the root cause. And this is what we need to solve.
Finding the root cause is no longer even just a single processor in a chip anymore, right? It's now, the root cause may involve software, it may involve multiple different types of cores, it may even involve multiple chips in a package.
Correct. So this is where the challenge is becoming even more difficult, is that as you bring in more and more software contents, there is certain non-determinism that come into the system because software is mimicking the real devices, and real devices by nature are asynchronous. So the timing of that is not determined. So we also need to bring in some sort of deterministic reproduction of the bug.
So what does this do in terms of total time to confidence in your design and time to sign off where you know it's going to produce a chip that's going to work?
So every issue that we are finding, the goal is to debug and to solve that problem. And in that sense, time to root cause becomes very important, because unless you can solve it in a time-bound manner, you're going to delay your chip.
So what's being done now, and where do we have to go to? Because you're no longer just dealing with a small piece, you're dealing with this whole thing in a system level context, right?
Right. So let's take a look at how debug is being done today, and to solve this problem, where we need to go. Let's do that. So again, going back to the previous picture, so we have billion cycles and billion gate design, and now you're looking for one gate and one cycle where it goes wrong. So this is nothing but a search space problem. And what better way to describe that than a simple graph theory example. So traditionally what has been done is what we call as waveform level debug. And let's look at the graph theory. So this is the diagram that I've drawn is more of a depth first search, where you are picking one particular node and trying to do deep analysis of that particular node. In terms of debug, what it means is that I'm taking a sample of 1 to 2 million cycles and I'm doing in-depth analysis to see if my failure is in that window. Now, if the failure is not here, I move to a different node and search here. If problem is not here, I move to a different node. And as you can see, that this process can take longer. Now, if I direct your attention to the problem statement that we drew, so let's try to draw to scale. So if this is 2 billion cycle, what we're looking at is probably 1 to 2 million cycles is going to be this much window. Now you can imagine how many iteration it is going to take me to get to the window where the cache error is. And hence, the summary of this discussion is that as the complexity is growing, this waveform level debug is not converging fast enough.
Why wasn't this done in the past? Is it just a function of more compute horsepower in order to get the problem solved?
So in the past, it was not needed, right? I mean, as emulation has grown, we started doing emulation at RTL level debug, right? And the designs were small and they were running millions of cycles. So the number of iterations needed were very minimal. And as we are growing in complexity, this is becoming a challenging problem.
So where are we now? What comes next?
So now we need to figure out how do we solve the problem. And what I want to do is I want to stick with the graph theory because that is really a nice algorithm to find a problem and define the search space. So I want to draw your attention to something that we call system level debug. And here the idea is that from depth first search, we move to breadth first search, and we are trying to analyze all the nodes in parallel. So the goal is that I want to see the entire graph, entire design over entire run and try and narrow down the problem through some high level abstraction of the system.
You talk about system level debug. How do you define a system here?
So now a very interesting question. So yes, the definition is there, but then the question is, as you said, what are the requirements, right? How do we define what does system level debug mean to us, right? So there are a few things I want to highlight as key requirements. The first and foremost is we need something as we are dumping the information of the design over the run. So we need something what I call as infinite depth. So essentially, no matter how big the design is and no matter how long it is running for, I want to be able to dump some abstract system level information for the entire design over the entire run. So that is the first requirement. It has to be what I call as infinite depth. Second key requirement is that you're trying to enable this during regression itself, right? You're doing some testing overnight, you've lined a bunch of tests, and the goal is that I want to reduce my time to root cause, so I want this abstract information to be available during the regression itself. What that means is that there has to be zero throughput impact. I cannot slow down, because if my performance goes down, then nobody would want to enable this. And the key aspect of that requirement is that to improve performance, number one, it has to be streaming, so that there is no hardware-software sync happening. You're not stopping the emulator to pass information to the Unix system or the disk. So it has to be streaming, and then it has to be at speed, so that your regression doesn't slow down.
And this is basically keeping your hardware active all the time, right? That's really what you're going for, uptime and throughput.
Correct. So as you're generating the system level information, your hardware has to be running all the time, continuously, no slowdown, no stops. And at the same time, the piece of the technology that is dumping this information out should be designed in such a way that it doesn't reduce your performance, right? So there is performance and there is throughput, and we want to create a system or a solution where we have zero impact to throughput and zero impact to performance. Now, from there, we briefly touched upon deterministic debug, right? So that becomes a third very key important aspect of it, that once you have found through this analysis, high level analysis, let's say that I figured out that I want to focus my debug in a particular window. Now, as I'm rerunning the test case to generate a waveform of that window, it is very important that I replay the design exactly same way as the problem happened in the first run. So deterministic bug reproduction is the third key important requirement for the solution that is needed for system level debug.
And really what you're doing with that is bounding the problem, right? That's a way of doing it and still keeping everything moving.
Correct. So the idea is that you never miss a transient failure. You hit a problem and then you can consistently, repeatedly reproduce the problem again and again and again. And then, so now that you've generated the waveform, you still need to find a debugger to see the waveform and debug the problem and find the root cause. And again, going back to, let me get back to the point here that we are growing in terms of software complexity and design complexity. So you have a lot more data coming out of emulator than what was happening before. And that means that you need to have a native integration of your debugger to the emulator, which can scale very well to this kind of complexity. So really the scalability of your debug solution or your debugger is really the fourth key requirement.
And so what you're trying to do is take more data, collect more data, but also be able to make sense of that data too, right?
Right. So this is where the system level debug becomes very powerful tool, that we are collecting a lot of data, but then through the trackers, monitors, checkers, we are trying to create a funnel and using that come to a point or find a window where the failure happens. So essentially, if you look at it, you actually only need 2 iterations to debug a problem. First one, where you've generated the entire system level information. You went offline, you analyzed the information, found the window, and then through deterministic bug reproduction, went in that window, did the waveform capture, and through native integration of your debugger tools, found the root cause.
Of the 4 points that you put up here, all of them have to work together, right? I mean, you can't just have one or the other.
Yes, that's the key aspect of the solution, because unless you have infinite depth, you're not going to get the system level view. Unless you have streaming of key signal at speed, nobody will enable this in regression, right? So you're losing, again, you're adding more iterations and you're lengthening your time to debug. If you do not have deterministic bug reproduction, then when you actually need to debug the problem, the bug will disappear, right? Or bug may disappear. That's the issue with transient failures. And unless you have a solution for waveform-based debug that is scalable to the complexity that we discussed before, again, that is going to fail. So all 4 of these requirements are necessary, and eventually with this requirement and a solution that is built around it, as I mentioned, that you get the system level view, and in less than 2 iterations, you can debug the problem.
Ribhu Mittal, thanks for a great explanation.
Thank you. My pleasure.